The question is, could you list the equations needed for coordinate transformation of strain? It turns out that the coordinate transformation equation for the components of the strain tensor are identical to those of the components of the stress tensor. In another section, we've covered the details of the coordinate transformation of the components of the stresses thoroughly, and therefore I will not repeat many of the details here. But to understand exactly what is it that we are talking about here, I'll show you the correspondence between the stresses and strains. And if you recall, with respect to a three-dimensional Cartesian coordinate system x, y, z, the components of the stress tensor is written in a matrix form like this. The corresponding off-diagonal terms here are equal to each other. For example, tau xy equal tau yx, and therefore this is actually a symmetric matrix, implying that there are actually only 6 independent components for the stress tensor, not 9, just 6. In a similar vein, this is the three-dimensional strain matrix. There are two things to note here. One, when it comes to shear strains, there are two definitions. The first one, called the tensorial shear strain, are the ones that are presented in this matrix. For example, epsilon xy is a tensorial shear strain. The second one is called the engineering shear strain. So the engineering shear strain that goes with epsilon xy is gamma xy. The relationship between the two is simply this. Gamma xy is 2 times epsilon xy. Now this is an important distinction when we get into the coordinate transformation equation. So keep that in mind. The second thing to note here is that just as in the case of the stress tensor, the strain tensor is a symmetric tensor as well. In other words, the corresponding off-diagonal terms are equal to each other. For example, epsilon xy equals epsilon yx, epsilon xz equals epsilon cx, and so on. So just like the stress matrix, there are only 6 independent components in this strain matrix. Of course, the diagonal terms here, which are epsilon xx, epsilon yy, and epsilon zz, are called the normal strains. Let's talk about the sign convention for the components of the strain tensor. We will stick to the same sign convention that we have defined in the section on strains. These are those sign conventions. When it comes to normal strains, tensile normal strains are positive. When it comes to shear strains, these guides here will tell us whether a given shear strain is positive or not. For example, if you have two perpendicular lines, one of which is in the direction of the positive x-axis, the other one is in the direction of the positive y-axis, then the shear strain will be positive if the angle changes like shown in this picture. Suppose say we have a long concrete dam like this one right here. As we will discuss in the next slide, this can be approximated into what is called a plane strain problem. We only have to consider the deformation of the concrete dam on this plane, on the plane YZ. Supposing say we take a little differential element on that plane, ABCD, and consider its deformation over here. If that differential element, which is originally a rectangle, deforms into what is shown by these purple lines here, then the shear strain is positive. Why? Well, if I look at point A, right, there are two perpendicular lines, one of which is in the direction of the positive y-axis, the other one is in the direction of the positive z-axis, right? So this is exactly like case 1 over here. If the angle decreases from its original value of 90 degrees, then the shear strain according to the sign convention is positive, right? And similarly, point D is like case 2, and point C is like case 3, and point B is like case 4. Let's say this is a parallelogram. That means this rectangle deforms into a parallelogram, right? That means these lines are parallel to each other and these lines are parallel to each other. Now you can see the final angle at this corner and this corner are equal to each other, the final angle is smaller than the original angle, and therefore according to the sign convention the shear strain is positive. And over here at these corners the change in angles are still equal to each other, right? But the final angle is bigger than the original angle of 90 degrees. But then, according to the sign convention, they are positive, right? So we make two key observations here. One, the shear strain is the same at all four corners, and therefore this little differential element experiences a uniform shear strain, gamma yz, right? The second observation is that the shear strain gamma yz is positive according to these sign conventions. Now let's review two common two-dimensional approximations. So we've done this in the section on stresses, so this is basically a review. Looking at this picture first, in general, the state of stress at a certain point can be three-dimensional like shown here, right? Suppose you say the deformation actually happens only in the YZ plane. Then the outer plane stress components would be these, this, and this. Each of these three stress components are in the direction of the x-axis, right? And if these two shear stresses are 0 and the normal component sigma x remains a constant during loading, then this is what is called the plane stress condition. Similarly, if the shear stresses are still 0, but instead of the stress, the strain is 0 in the direction of the x-axis, then this is called the plane strain condition. The equations that I'm going to talk about in the next couple of slides will correspond to this case here, plane strain case. So in this case, we only have to worry about these three strain components, epsilon y, epsilon z, and gamma yz. So out of the 6 independent components of the strain tensor, these are the only non-zero strain components, and therefore we only have to worry about these three strain components. So let's briefly remind ourselves as to what is it that we are trying to achieve here through coordinate transformation. We know the three strain components in the xy coordinate system, the two-dimensional Cartesian coordinate system, and we are trying to find the strain components in a rotated coordinate system x prime, y prime, where the x prime axis has been rotated counterclockwise from the x-axis through an angle theta. In other words, we are trying to find a relationship between these and these. If you recall what we did in stresses, there are two general approaches. This is true for the strains as well. The first one is the mathematical approach, where we derive equations between these quantities and these quantities. The second one is the graphical approach, and the specific approach we use is called Mohr circle analysis. In the section on coordinate transformation of stresses, we went through the details of the derivations. Here, for simplicity, I'm going to skip. Also note that the derivations are not identical. They are fundamentally different from each other. And if you are interested, I recommend that you refer to a book. But amazingly, we arrive at the same equations, and I'm going to show you that in the next slide. The strain analysis can also be conducted using the Mohr circle principle, but I will not cover that here as well. In this slide, I managed to squeeze in all of the important equations, not only for the strains but also for the stresses. I did this so that you can see the relations between the two and convince yourself that the equations are identical. And if you recall, in the section on stress, we had two forms of these equations. The first one is the more elaborate, detailed form. The second one is what I call the compact form. The compact form is a lot simpler, so that's what I have here. In the compact form, we define four different quantities here: sigma average, little a, little b, and r, like shown here. Once you do, the equations for sigma x prime, sigma y prime, and tau xy prime are these. In the two-dimensional state of stress, there are two principal stresses sigma 1 and sigma 2, which are given by these equations. We also calculate two angles, theta p and alpha p, one of which is supposed to go with one of these, but we don't know which one goes with what, right? So I'll make a comment about that in the next slide. Finally, the maximum shear stresses are calculated by these equations, and once again there are two angles to go with them. Now let's look at the details of what I have on the right side column here. We define these four parameters in exactly the same way as we have defined over here in the case of stresses. Epsilon average is simply epsilon x plus epsilon y over 2. Little a is epsilon x minus epsilon y over 2. Little b is epsilon xy, not gamma xy, it's epsilon xy. So if you are working with gamma xy, then you need to divide that by 2 in order to define little b. R is then square root of a squared plus b squared. I make a little cautionary note here. So this is one place you want to be careful as you go from the stress equations to the strain equations. Now once you have defined these parameters, now you can see the strain components epsilon x prime, epsilon y prime, epsilon x prime y prime are given by exactly the same equations as those for the stresses. And here too, note that we are not calculating gamma x prime y prime, we are simply calculating epsilon x prime y prime. The principal strains epsilon 1 and epsilon 2 are given by these equations, which are identical to these equations. The maximum shear strains are given by these equations. Once again, what we are calculating are the maximum values of epsilon xy's and not gamma xy's, and that's why we have a factor of 2 here. And in the case of principal strain, there are two angles, theta p and alpha p, and they go with these principal strains. And in the case of maximum shear strain, there are two angles, theta s and alpha s, they go with these maximum shear strains. We'll talk about which one goes with what in the next slide. To sum, you can see that the equations for the strains are identical to the corresponding equations for the stresses. So only thing you want to keep in mind is that wherever you see tau xy in the stress equation, you want to use epsilon xy, not gamma xy. Just to emphasize that point, I made a note of that over here. Now let me return to my comment about the two angles that are calculated for the principal stresses and principal strains. We said we don't know which angle goes with what, right? If you recall, this is how we resolved it in the case of stresses, and this is how you resolve it in the case of strains as well. So what you do is you take one of these two angles, say theta p, and substitute that into the transformation equation for epsilon x prime. And if epsilon x prime works out to be epsilon 1, then you know theta p goes with epsilon 1. And similarly, if epsilon x prime works out to be epsilon 2, then you know theta p goes with epsilon 2, not epsilon 1. And of course, the other angle, alpha p, goes with the other principal strain. We have the same problem in maximum shear strains, and we will solve that problem in exactly the same way.